Hi and welcome to this lesson on fuel cells and half cells. So in the last lesson we finished off learning about Kp and how it changes with temperature and doesn't with catalyst and pressure. This is a new topic, so make sure you check through all the slides before you have a go at any past paper questions. Our key learning objectives. Today we're going to look at what half cells are, and then we're also going to take a look at how to make a full electrochemical cell. Something that's essential for understanding this topic is to remember that the reduction is the gain of electrons and oxidation is the loss of electrons. I'm sure you've come across the really useful acronym OIL-RIG. So oxidation is loss of electrons, reduction is gain. And when we've got a reaction where reduction and oxidation occur simultaneously, we call that a redox reaction. And that is what we're going to be looking at today, applications of redox reactions. The oxidation state of an atom or an ion, it tells us a measure of how oxidized or reduced it is. So oxidation involves the increase of the oxidation number or the oxidation state, and reduction, clue in the name, so it's quite nice to reduce, shows a decrease in the state of the oxidation state or the oxidation number. A redox couple. So this is the combination of two forms of the same chemical species separated by the gain or loss of electrons. So that they have two different oxidation states. And an example, we've got one here. So this is copper metal and copper ions. So they are a redox couple linked by the gain and the loss of two electrons. And this is the half equation that represents that. So this is the reduction of the copper ions. They are gaining the electrons. Reduction is gain and forming the solid copper. And if the reverse happens, then we would have oxidation happening. We can create a dynamic equilibrium. And how we do this is we dip a rod of the metal into a solution of its own ions. And this is called a half cell. So these are two separate half cells. So at the moment they're totally separate. And they're both two different examples. So I've got magnesium, a rod of magnesium in a solution of Mg2 plus ions, and then I've got a rod of copper in a solution of Cu2 plus ions. If we go back to that image of the copper rod in the copper ion solution, an equilibrium is established. And I can write this out as the equation. So Cu2 plus 2E minus gives us a solid. And I'm showing a dynamic equilibrium that's formed by using this arrow. So the rate of electron loss is equal to the rate of electron gain. That's what that means. So the position of the equilibrium varies for different redox couples. So where that equilibrium, whether it lies to the right more or the left more, and a more easily reduced metal. So in this image here, we've got reduction happening. If we're thinking about it as the forward reaction is reduction, the more easily reduced a metal is, the further to the right that position of equilibrium will lie. In that previous equation, we could see that since copper was gaining electrons, 2 electrons, then that is an example of reduction. So those copper ions were being reduced. And in the reverse reaction, from the way that I'd written it, the solid copper was losing electrons, and therefore the backwards reaction in that case was oxidation. And you saw the sign that I used. So we've got an equilibrium, a dynamic equilibrium, and I show that the reaction is reversible. So I use this symbol to represent that. So at equilibrium, that metal strip or that metal rod that's dipped in sets up a potential between the metal and the ions in the solution. And the greater the tendency for the metal to lose the electrons, the greater the potential. And we cannot measure the potential of a single half cell by itself. It's not a complete circuit, so nothing's going to come through on that voltmeter. But we can measure the potential difference across two half cells. So we need to learn how to connect those together. So far we've discussed one type of half cell, the one where we put a metal strip in a solution of its own ions. But there's actually two more types of half cell that you may come across, and it all depends on the state of the redox couple species. And here we have a new type of half cell. So this is where, in terms of our redox species, one is a non-metal, so it could be a gas, and the other one is a non-metal ion, so a solution of the ions. So in this particular case, we're going to use a platinum or a graphite electrode, and we're going to dip it into the non-metal ion solution. And the non-metal gaseous element can then be bubbled through that electrode. And I'll show you an image of that shortly. And the third type is if both of our redox species on both sides of the equation are ions, aqueous ions. So this half cell contains two solutions of the different ions in our beaker. And for example, we could have Fe2+, and its redox pair is Fe3+. And again, a platinum or graphite electrode is used in that case. Here's the first type, so the type that we're familiar with. You can see we've got our metal strip in the solution of its metal ions, and here are our two new ones. So we've got a non-metal, our gas, our chlorine coming through, that's one of our redox species, and then it's going to be, we're going to have our platinum electrode dipped into a solution of its ion through a gas delivery tube. That's what we call this structure. And then our third type was where both of the species in the redox couple were ions. So we've got a solution of both of those ions, and we've got a platinum electrode being dipped in. So why do we use platinum and graphite, for example? Well, they're good conductors. They're very good materials. They conduct electricity very easily, but they're also inert. So they're not going to get involved in that equilibrium at all. So they don't react with any other components. Of course, I'm sure you've heard that platinum is a very, very expensive metal. Graphite is a lot cheaper, so it's much more commonly used in electrodes. An electrochemical cell is formed when we join two half cells together. And we need to use a salt bridge, which is a piece of filter paper, usually dipped in a potassium chloride solution or some sort of salt solution, and that allows us to complete that circuit and for the ions to keep or to carry that charge and to keep that flow moving. We ensure that the salt bridge is made of filter paper, not metal wire, because that avoids creating, well, a metal wire, it would create metal potentials in the circuit, and that might affect the measurement that we get out of our voltmeter in our electrochemical cell. So we use a salt bridge instead, and it uses a salt that's not going to react, and it's not involved in the equilibrium. Here we've got an example of an electrochemical cell with two half cells joined. We've got the zinc half cell and the copper. And I'm going to label our parts. So of course we've got our wire here and we've got our voltmeter. This is going to be our copper solid electrode, and we've got our zinc solid electrode, and we're going to have a solution of zinc ions. They're going to be aqueous, of course, and then we've got our copper 2+ ions. And let's not forget our salt bridge. You can see here that our zinc electrode has a greater tendency to lose electrons than our copper electrode. And if I write the equation that's happening at the zinc electrode, we've got our solid zinc losing electrons and becoming our aqueous zinc ions. So that's not the 2E-, it's not actually shown there, but that's what we're going to have. The voltmeter up here needs to have a high resistance to prevent current from flowing so that the voltage can be measured. If the voltmeter were removed, then we would have the electrons flowing from the zinc to the copper electrode. So in that particular case, we would have zinc metal. It'll lose electrons. Oxidation is loss. So we'd have it being oxidized, and it would form zinc ions. And you saw me write that equation on the previous slide. And at the copper electrode, we would have our copper ions gaining electrons, so being reduced to form copper metal. So how would that look over time? Well, over time, we've just discussed the fact that we would be losing our zinc solid as it gets oxidized into the ions. So we're going to get a reduction in the size of the zinc electrode. And at the same time, we showed that the copper ions, it was being reduced, so they were gaining electrons and so becoming copper solid, like the metal, and we would get an increase in the size of the copper electrode. So we can see this electrode is growing, and this electrode, our zinc one, is going to be shrinking over time. We will also see that our zinc half cell will be increasingly positive and our copper half cell will become increasingly negative. And this is going to prevent electrons leaving the zinc electrode and moving to the copper half cell. And just a reminder that our salt bridge contains inert ions, and what they can do is they can move and balance the charges, and that allows the cell to keep working.